The first distinguished speaker is Professor Eitan Tadmor from the University of Maryland. Professor Tadmor is a distinguished university professor at the University of Maryland. He is a renowned mathematician. He has made fundamental contributions to many fields, including nonlinear conservation laws, kinetic theory, and more recently, collective dynamics, which is related to today's talk. Professor Tadmor has received numerous awards and honors, including the and RCM invited speaker back in 2002. And more recently, the SIAM ETH Heinrich Prize, the Nobel winner prize last year, I think, and also the Gibbs lectureship, and the list goes on. Without further ado, let's welcome Professor Tadmor.
Thank you. Thank you for coming. Okay, I would like to share with you a work that we have done in the last couple of years, which has to do with non-convex optimization based on a swarm-based approach. So let me start at the beginning. The objective is to find the minimizer for a given function f in RD. And the starting point for optimization is the gradient descent method, which was introduced, by the way, by Cauchy in 1847. The gradient descent method actually finds not the minimizers, but the minimal critical point, which is there. And the idea in the gradient descent method, as we know, is that we proceed in the direction of the gradient of f. So if at time tn we are at the position xn, then we take a step of size h in the direction of the minus the gradient of fn. It's actually interesting to read what did Cauchy wrote in 1847 when he invented the method. And he wrote, "I will restrict myself here to outlining the principle underlying my method, with the intention to come again over the same subject in a paper to follow." But he never did. So it is impossible to explain or to try to cover even the impact of the gradient descent method. But we will all agree that in the gradient descent method, once we decide about the direction, the only thing that remains to be done is the protocol to choosing the step size. And why the gradient descent method? Because we really have the following important statement that I will make reference to. Here's the statement. For any fraction lambda less than 1, there is an age lambda, a threshold, such that for all step size less than this threshold, you go down. And the amount you go down is lambda times age, the square of the gradient. And the reason is because the linear part dominates over all the other terms. That's basically the essence. And that's basically very beautifully explained in the paper of Cauchy. It's quite interesting to read it, right? 1847. And in the hundreds of years since then, essentially there were different developments in coming with protocols. So the different protocols for stepping for age lambda, which age depends on position and lambda, backtracking, and more recent, the other method, and sort of depending on a momentum. And here's a more recent work by He-Liang Liu. I mean, these 3 dots, of course, covers a whole branch of mathematics. What I would like to do in this talk is to come with a completely different approach, which is based on swarm. So in order to describe this method, without further ado, let me tell you what this method consists of. It consists of 3 main components. The first component is this, that we do not have one agent, we have a swarm of agents. And each agent is in a position x, xitn, this is the agent, and each agent, that's extremely important, has a mass. weight. So these are the masses which are denoted by MITN. So this is first component. Second component, communication. Every agent has to communicate with all the other agents in the following manner. We always compare, that is, we are part of the swarm, who is right now the lowest agent. And everybody has to give a part of its mass to the lowest agent. This is what it says over there. If I'm agent I take a fraction of my mass. This is this number eta, which will be here in red. And I take a fraction of my mass. I have now a less mass. And this fraction and all the other fractions are added to the guy that is staying at the position IN. IN is the position of the guy or the agent that stays at the lowest point. Now, what is this fraction? The fraction depends on the relative height. So if you look at this fraction, it's basically the height of agent I minus the minimal height relative to the total variation of the heights. So this is always a fraction between 0 and 1. And we give this fraction of my mass to the guy that's staying at the bottom. So there is a constant transfer of mass from top to bottom. Okay. And then the third component, every agent now has a mass. So we have to move in the gradient direction. But now what is the protocol? So there is a protocol here which depends now on your mass. I will describe the protocol in a second. In fact, it does not depend just on your mass, it depends on your relative mass, your mass relative to the heaviest element. I have now to arrange all these agents and to see who is the heaviest and who is the lightest. So there is an interplay here between positions and mass. I embed the whole problem in a larger dimension, which include the ambient space plus the mass space. Okay, let me now tell you about the time stepping. The protocol for choosing the time stepping, which is called learning rate, by the way. I will not talk too much about machine learning. This is unacceptable. But anyhow, let me tell you what is the protocol. We know already that we have that from the gradient direction, there is this kind of decay, which I mentioned earlier. So there is an age and there is an age lambda, age depending on lambda, which is sort of the threshold, the largest step where you actually going down. Observe that this function as a function of lambda must be a decreasing function as lambda, right? If I increase lambda, then clearly the threshold is going down. So what I will do is I will take, instead of age lambda, I will take age of lambda times my relative mass. That's it. That's the rule. Your step depends on the mass. Now let's see the consequences. The consequences is that there is a dynamic distinction between the heavy agents and the light agents. The heavy agents, those whose mass is almost the maximal mass, which is denoted here by plus, will take smaller time steps. If you are heavy, you go with small time steps. This is an indicator that heavy agents are close to the desired global minimum. If you are lighter agents, on the other hand, you are allowed to take large time steps. You are literally not a leader, you are more explorer. So dynamically, there is a change between leaders and explorers. Now, in this process, each agent, we remember, sheds an eta fraction of its mass to the current minimizer. You remember that? If I'm really high, I have to take most of my mass and to go, that will go away. If I'm very close to the bottom, then only a small fraction of my mass is eliminated. In particular, the agent, which is the worst, the highest, will eliminate all its mass. He will be dead. So only the most, the fittest will survive. And in every stage, the number of agents will go down by 1. Okay. And finally, we notice, since I always take my mass and I bring it to somebody else, the total amount of mass is conserved. Let's assume that it's 1. So we conserve the mass. So in fact, the mass could be viewed also as the probabilities to identify the global minimizer. So this is the process. These are the 3 components. We have agent with mass. The masses always go down, and depending on the mass, you take a small or large time step, or you eliminate it completely, while the total mass is conserved. Okay, now let's see an example how it is working in action, and then I will tell you about many other things. So first of all, why communication is so important? Remember, there are agents, communication through mass, and the time stepping. Why communication is so important? So you can say, well, we can have each agent, and each agent will go by itself. No. The communication is so important. Let's take even this simple function that you see in front of you here. It's enough to demonstrate the complexity of finding a minimizer. So here's stage 0. This function that you see here is given here. And now you see the initial positions of some masses distributed here. Now, why not all the masses are the same? We begin when the masses are the same. But if the position is too close, then we conglomerate, we put them together. And that's the reason that you see here sort of collection of different masses. They just happen to be so close. So we put them together. So this is the initial iteration. And then with the initial iteration, we just take the recipe of, depending on the mass, to take the steps. You remember the heavy agents, they take a smaller step. The lighter agents, they take a larger step. And let's see what happens after one step. After one step, some of these agents, they jump arbitrarily, and this is the position. You can see, as is well known, you can see that this is the relatively wide valley here. This is the most dangerous place, you might think, because, you know, when you have wide valley and then you are trapped in a region when you get a critical point, then it's very difficult. You have to push the agents from here in order to get to a smaller point, a smaller ground, a lower ground. Okay, so this is step number 1. Now comes steps number 2. It's interesting. Pay attention. You see, these agents, they start to go down. So are these other agents. But it's more important that since, for example, this is higher than this one, part of its mass is going to this one, right? So this part of this mass and this mass, all these agents will shed part of their mass to the lowest one, which is here. And indeed, this becomes heavier, this becomes lighter. And so are these, they become lighter. Everybody else becomes lighter. So this is the second stage. The third stage, we continue. Aha! Now you can see that some of these agents are here. This is still the heaviest, but you know what? This is not the lowest, because this is actually the minimizer. You can see that here you have agents which concentrate in this big valley. This is still the heaviest. This is still the lowest. And you get all these agents which are scattered around. Let's continue. You can see this red dot. Each time the red dot comes to you, it means this is the survival of the fittest. We eliminate you because you are at the top, right? Okay, so this red dot on the top, you can see that you get now one agent which is reasonably heavy, but still it's on top of this and on top of that. This is still a heavy agent, and it will stay a heavy agent because even though it's not as low as this one, I mean, the difference between them is almost negligible. So it will be very difficult to get rid of this stubborn local minimizer. Next, you can see that the survival of the fittest continue with this red dot. Now we have less mass here. It went actually to here. But this is still the heaviest because very little mass shed from here to there. I mean, and you get all these other agents which are floating around over there. How are you going to get rid of them? Well, you can see what happens with the survival of the fittest. Still, more mass is accumulated here. This is now lightest, right? It's lighter than before. Next step. Okay, we are here. Very tiny mass is still there. Next. Well, we will not get to there because we stick here. Now we get to here. This is the higher than this one. It will be eliminated. There is almost no mass there. Still, these two are the heavy competitors. Next, now we kill this by the survival of the fittest. Final stage almost. And we are still here. And now there's an issue. How are we going to get rid of that? We are never going to get rid of that, because we are not pushing it. This is the deterministic method. It's not stochastic. The next step, now the survival of the fittest wins. All the mass from here went to that, and we are done. So this is the story about this swarm-based gradient descent method. Now, let me show you something. We compared it with other methods, stochastic or not. So here's the gradient descent method just with a fixed step size. This is the gradient descent method with eta equal to 0. You know what is gradient descent method with eta equal to 0? That there is no communication. You can say, well, is communication really important? Do I really have to talk to the other? So let's assume that each one does its own thing. This is what you see here. And these are the other methods that I will not describe, but this is sort of the running minimizer in the literature right now. And as you can see, when you get 10, 20, or 30 agents, the success rate is essentially the same. This is our method. I mean, there's no difference. 100%, 95% is not interesting. The point is that in all these methods, even though these are the usual one-agent method, so what we did in this case, we just put many agents, 10, 20, or 30, we just spread them around and let them run. But we spread them in the interval -3, 3. You know why we did -3, 3? Because we knew that the global minimum is in the interval -3, 3. So you actually enclose where the minimum is. But in general, you don't know where the minimum is. So we made another test where we threw all the points in the interval -3, -1. And in -3, -1, this is away from the global minimum, and somehow you have to extrapolate where the global minimum, and now you see a big difference. Because the swarm-based dynamics has these explorers, not the leaders, the explorers that always go away and they try to explore for the swarm. Where the other method, I mean, once they are stuck somewhere, that's it. There's nothing you can do. So there's a big difference. And we keep repeating this idea that we do not know the general region of the global minimizer, and that's where the difference shows up. Okay. I should mention, I mentioned just one agent optimizer. Of course, there is a whole class of global optimizers depending on swarms, and there is not enough time for me to cover everything. I just mentioned here, first and foremost, the consensus-based optimization. Where is Oliver? I don't know. Anyhow, which is important, but there's two fundamental differences between the CBO and what we are doing here. The CBO, on the one hand, does not require the use of the gradient. On the other hand, is a stochastic method. That is, it's not deterministic. And it's based on the Laplace principle. So you have to do a very important tuning with this parameter alpha. Then there is a whole sort of biologically inspired method, the ant colony optimization, artificial bee colony optimizations, you name it. There is the particle swarm optimization, which is very close to what's going on here, except that there is no communication. Communication is the key element. And then there is, of course, simulate annealing and so forth and so on. I just made the reference because it's an educated lecture, but I will not have time, of course, to discuss or to compare. What I would like to do is to give you one slide of this SBGD method. So everything I described really enters in one slide. Here's the slide. Basically, you initialize, all the masses are the same, and then if the masses is too small, then you set it to be 0. And then you reduce the number of agents. You know why? Because of survival of the fittest. Here, each agent sheds a fraction of its mass, right? This is the fraction. What is the fraction? It's this eta I that I had before. In fact, the fraction could be taken to be any power of the fraction. It's still a fraction. We didn't optimize, but we found out that in general, p equal 2 is sort of to be, in some global sense, better. So we use always p equal to 2. And then all these masses that were shed from different agents move to the agent, which is current minimizer. And then once we have this rearrangement of masses, then we take a step, and the step is in the gradient direction with a step size h, which is dictated by something which is called the backtracking algorithm, which I'm going to describe in a second. I still did not tell you precisely the protocol for the step size, but it depends on the mass. That's important. And this is it. This is what you see here, nothing more than this one step. Okay, now let's talk a little bit about the step size and quantifying the descent property. So let's assume that our the function f, the Hessian has a bound L. then we know that if you expand it, this is the expansion, and this bounds the Hessian, then we get this kind of an estimate. And this tells you that if age is small enough, this is exactly what I said before, if age is small enough, then this is bounded by a fixed number, and you get this decay which has to do with lambda times age gradient f squared. Instead of taking lambda, we now replace lambda by the relative mass. It's still a fraction. So this is the basic statement of this SBGD method. So let me repeat. Every step that we do, this is sort of, I insist on that. Every step that we do, we always go down, no matter what. If we don't go down, I forget about the system. I don't accept it. So I always want to go down, a little, a more, I want to go down. How much do I go down? I go down by amount which has to do with the step size times the lambda times the relative mass. So if the relative mass is small, okay, we go down less. Going down means basically the loss function, as it's called. If the mass is the relative mass, if we have heavy agent, then of course we go down by a larger amount. Now, we have to play with this age lambda. The age lambda need not be small. So how do we find this threshold? So the idea is to find the largest time step which allows this property to hold. How do we find the larger time step such this property holds? It goes by something which is, particularly we don't have access, of course, to the Lipschitz bound, by a backtracking. So let me tell you about the backtracking because it's nice. The idea with the backtracking is this. You test when you have the reverse inequality. This is not what I want. I want the other inequality. So I start with age, which is large, 100, and then I ask, is it true that this inequality holds? Well, as long as it is if it holds, then I take a smaller age by a factor of gamma. Where is gamma? Here. So I shrink my age, I go back, until finally, this inequality, the wrong inequality, fails. Namely, we get the other inequality. And then I stop. And this is my time step. And why this is so important? Because I claim that my time step, which comes from here, satisfies not an upper bound, but a lower bound. My step cannot be too small. Why is this true? I claim that this step cannot be too small because of the following reason. You see, age over gamma must have this lower bound. Why? Because, you see, because we know that we fail this inequality. This inequality is satisfied not for age, but age over gamma. Now, because of the descent property, what we get is that age over gamma cannot be too small. If it will be too small, then we will have the reverse inequality. So, since we have this wrong inequality, the step that we are having cannot be too small. So without accessing the Lipschitz bound, we know that by this backtracking, our step size is at least having this kind of size, which has to do with the mass, relative mass, and the Lipschitz bound, even though we do not have access to the Lipschitz bound. Now, once we know a lower bound for the step size, then of course, we know how much we go down. So here's the statement. At every stage of SBGD method, we go down by the amount which has to do with 2 gamma. This is a user parameter, less than 1. The Lipschitz bound, which we do not have access, but it's still there. And then this product of these relative masses. Okay. So let me now, I have 45 minutes, right? No, I have 1 hour. I have 1 hour. Is that correct? Yes. Okay. See if I have 1 hour, so I will do something I have not done. Let me show you now a proof that this deterministic method will always converge. It's actually interesting, not just because of the proof, because the proof tells you what is the logic behind this SBGD method. So there are 3 cases in this SBGD method. The first case is when the lowest agent is also the heaviest one. This is the ultimate situation. You see, the canonical scenario is that the minimizer, which I always denote by minus here, xin is the minimizer at time stage n, is also the heaviest. So you remember we have to take here the relative mass. Well, the relative mass for the heaviest is 1. So clearly, we know that at time n, we dominate with this kind of descent. We dominate f at xin, but f at xin at the next time stage, this need not be the minimizer. but it's clearly larger than the minimizer wherever it is, because the minimizer is the minimizer. So we get that f at x minus at n plus 1 is less than f at x minus n minus something. I just need this something. Okay, but this is only the ideal scenario when the heaviest is the lowest, and we saw that this is not always the case. So now we have to take two more cases. If not, then we know that our lowest agent, it's not the heaviest, but it got an eta fraction of the mass from a heaviest agent somewhere. It must get a mass. So this means that the mass of the lowest agent, this is it, the mass of the lowest agent must be larger than this eta plus fraction of m plus n. So what is written here, here's the heaviest agent, we don't know who it is, and fraction of its mass went into this lowest guy, because this is the recipe that we move mass. As a result, the relative mass has this lower bound, which has to do with fx plus and fx minus. M is the total variation, f max minus f minus. So this is the minimizer at time n. This is the heaviest. It's a little bit confusing. This is the heaviest at time n, and their difference satisfy a lower bound for the relative mass. I have to know what is the relative mass of my agent downstairs. And now there are two cases. Let's assume that this ratio is either bounded by something or bounded or is above something. The something is given here, whatever it is. Now, when we take this number, then I compare, don't look at this, look at that. I compare fx plus, this is the heaviest element, with the time n plus 1, which is of course less than fx plus n, minus twice this number, because this is the heaviest element. And this is always, for every agent, we go down. But I already know that fx plus is bounded by fx minus with this exactly one half of this amount. So at the end, I get that fx plus at n plus 1 is less than fx minus with this quantity, and this dominates fx minus at n plus 1. So here's the statement, fx n plus 1 is bounded by fx minus n minus something. And finally, what happens if this difference is greater than what is written here? Well, in that case, I take this difference, I do some calculations, and what I conclude is that fx minus at n plus 1 is less than fx minus at n minus something. And why do I elaborate all these three cases? Only for one reason. In these three cases you see in red, you see that it reads fx minus at n plus 1 minus fx minus at n minus something. These are the three cases. So this means that I can do a telescoping sum in n. And all this going down by something could be summed up to something which is finite. And this is exactly the theorem which says that if you sum the minimum between these three quantities, these are the three quantities that quantify how much we go down, it has to be a finite amount. And if this sum, of course, sum is finite, so these terms are summable, it means that these numbers should go to 0. And we get a limit set of minima of equi-height. So basically, our SBGD will converge to a critical point, or one or more critical points. But if it's more than one critical point, it's the unexpected situation where they have the same height. Because if one is lower than the others, well, you have to go down. I told you I always go down. I enforce going down. So this is the theorem of convergence. Which is, pretty remarkable, but there's only one problem with that. It has no idea about the convergence rate. So let me go now to another theorem, which actually quantifies the convergence rate. To do that, I have to estimate now the local rate of convergence for this SBGD by something called Lozasiewicz bound. At this point, I have to stop, as I did in another lecture, and I have to ask you, who knows what is Lozasiewicz bound? Anyone has heard about Lozasiewicz? No? No?
I have heard, but for this method, I don't
Yeah. So
I cannot tell you what it is.
Yeah. Okay. So let me tell you what it is. Now, what is remarkable, until 2 years ago, not because of this, because I'm teaching numerical analysis, never heard about Lozasiewicz. Lozasiewicz, in 1967, he came with the following, well, it's not exactly this, but he came with the following bound. This is a fundamental property of analytic function. It has nothing to do. In 1967, it's a fundamental property of analytic function which basically measures the following statement. If you have a critical point basically you see this. You want to quantify how flat is this. This is Lozasiewicz bound. It tells you the following. If you have an analytic function, and x star is a critical point where the gradient is 0, then there is a neighborhood of this x star such that fx minus fx star is up to a constant bounded by the gradient at point x to the power beta. And beta is a number between 1 and 2. It's easy to prove in 1D. It is in French, and it's an IIGS publication which I could not follow for multi-D. And basically this parameter beta, I wrote here in quotation mark, is the m is the multiplicity. It's m plus 1 divided by m. Sort of, you have to think about it like that. So it's a parameter between 1 and 2. And 2 basically means that you get a simple root, it's convexity. And as you go to 1, you get something which is becoming more and more flat. And this is a fundamental property of all analytic functions. And trust you me, once you have that, you can quantify the convergence rate of many iterative methods for analytic functions. Anyhow, it goes way beyond just the Lozasiewicz bound, beyond of course, application here, but I found it interesting. I thought that we should study this in calculus because it's a fundamental property of analytic functions. At least for 1D, it's not that difficult to prove. Anyhow, we have so let's see how do we use it. So we know about the descent property, right? At the next time step, we are less than what we were before, minus lambda h minus the gradient of f squared. Good. Take this inequality and subtract the f star alpha. Alpha is one of these possible limits because now we may have many critical limits. So subtract f star alpha from both sides. Great. Once we subtract the f alpha from both sides, then of course this difference between fn alpha minus f alpha can be estimated in terms of powers of the gradient at the point x minus alpha here, right? So that's essentially what is written here. This is this estimate. And when you look at that, this is nothing but a discrete Riccati's inequalities. In fact, if beta equal to 2, you solve it by Gronwell. If beta is less than 2, you get a Riccati inequality. And here's the theorem. For analytic loss function f with a minimal flatness beta between 1 and 2, the SBGD minimizers locally satisfy the following. Either they decay exponentially fast when beta equal to 2, expected. When beta is less than 2, they decay with polynomial rate at this rate. Okay, so now let's go to simulations. So let me show you a few more example simulation because we have to expand the discussion now. Here is this Ackley function, I think it's called. And you can see this one-dimensional. We will get to multi-dimensional in a second. And what we measure here, we took 200 runs. So we randomly spread the points and we take runs, and we would like to see what is the success rate. So what happens with the success rate, and that's interesting, we know the trick that the minimizer here is 0, and if we will spread all the points equally between -4 to 4, I know that I will converge with all methods. The idea is what happens when we are away from this 0. So what we did not take this function, we shifted by a parameter b. b equal to 0 is what you see here. b equal to 5, now this function is moved, and then 15, and then 25, and then this means that we need to extrapolate further and further to get to the global minimum. So you can see here that the success rate, depending on the b, is decreasing, well, depending on the number of agents, as we shift the b's in this case. Okay, here are the parameters if you're interested. The shrinkage parameter is 0.9, and the descent parameter is 0.2. Okay, fine. So what you get here is on the left the SBGD, and on the right you get essentially the gradient descent with no communication, and you can see now the difference that this actually does converge and this does not, particularly when B are large. When B equal to 0, there is almost no difference. Okay, so we wanted first of all to secure our understanding that communication is important. And here's what you see, all these dots, they try to jump over, and you know how they do it, with this transfer of mass, and this is how, this is a little bit fast, but you can enjoy, I hope. Yeah, right? So there is this survival of the fittest. There is always competition with mass going around until eventually it gets to the bottom. Okay. Let's move to two-dimensional case. So this is this is a much more complicated function, the restriction. It's two-dimensional. Even though it's two-dimensional, it seems, oh, just two-dimensional. No, this is not trivial because it has many local minima and they are very close to each other, as we shall see later on. And again, the same story, the initial data uniformly generated in -3,3. -3,3 encloses the global minimum. And we compare SBGD1, SBG2. This index is the power that I mentioned before. Gradient descent with a fixed step size, gradient descent with no communication, Adam method with various steps that I will not get into. And you can see the success rate roughly, if you're asking me, the same. I mean, you see the 2 is better than the 1. I don't care all these things. These are not. One important thing in this business, which I try to avoid, I do not like to optimize parameters. I just like to take something which is very rough and to understand what is really the behavior. So, yeah, I got it. Now we take the points and instead of -3,3, we put in -3, -1. So the method really has to extrapolate, and you can see that there is a big difference. Where the SBGD has this high success rate, you see everything drops because all these methods, Adam 0.8, I will not get into the details. You really have to get out of your way, and in order not to be stuck in some local minimum. And of course, the success of the method of the SBGD is not the leaders, it's the explorers. Without the explorers, it will not work. Here's the 20-dimensional simulations. The 20-dimensional simulations, what we measure with different shift, we measure the, is this the loss function? No, it's still the expected value of the error, only the first component, because we were ashamed to put many components because then the error really starts to grow. It's very difficult to get the right answer. So the first component you can see here in 20-dimensional shifted Ackley by these backtracking parameters as usual given here. And you compare the SBGD, the gradient descent with no communication, and the Adam, and okay, fine. But then it's dramatically changed, I think here. What's going on here? I think, well, I did not record it. This is the 20-dimensional, right? 20-dimensional. Sorry, this is the Ackley function. This is the restriction function. That's right, I forgot. The Ackley function, there are two functions that you didn't pay attention to. You will see in a second. The Ackley function is a little bit more user-friendly. But this restriction function, you can see that all our great effort was, was not that successful. It's very difficult to get into the global minimizer when you have a large shift. And you will see in a second why. So this is the 20-dimensional problem. And indeed, we also measured the loss. So as you know, in machine learning, they are not interested to find the global minimum. What they really want to make sure is that you get as low as possible. They don't care. You can be far away from the global position of the minimizer. As long as you are low enough, that's what really matters. So we measure here the loss function. And we convinced ourselves, okay, this restriction function is not a trivial test. It's not a trivial test. So why is it not a trivial test in 20 dimension and so forth? The reason is that when you have many dimensions, you really have to know where to go. You really have to know where to go. It's very difficult to visualize when you want to minimize a function on 20 dimensions. So you say, well, at every point I go in the direction of the gradient descent, which is the steepest descent, and I just tell you how I do it depending on the mass. But is the steepest descent correct? When you are very close to the minimum, that's fine. These are the leaders. But when you are away from the minimum, who said that you should go in the steepest descent? This is a fundamental question. So I overruled and I said that we will not go in the steepest descent. The only thing I care is that we will go down. Not the steepest, but we will go down. We will go down, but in a manner that we will explore the space in a better way. So how can we go down and explore the space in a better way? So this is now this chapter where no one has gone before. So the idea is that we take a step, the direction which I call P. And the direction P will not be the gradient descent. The direction P will be such that star will hold. So the direction P, I will call it this condition. It's an alignment with the gradient descent. So P cannot be completely orthogonal to the gradient descent. It should be aligned, and it should be greater equal, this inner product greater equal, or their orientation greater equal than 1 plus the relative mass over 2. So for example, if you take the heaviest element, the only way to satisfy that, if you normalize it to 1, the only way to satisfy that, you have to take the gradient descent for the heaviest element. But for the other elements, which are the light explorer, well, I don't mind that you'll go aside. How much aside? Depending on the mass, all the way to a factor 1/2 rather than 1. And this secures 1/2 of descent property. So if you make the expansion, here's the expansion, but now you see the P is not the gradient. So this is not a negative term, but it's as before, but it is still negative term because of this condition. And you collect all the terms, you can see that it's exactly what I had before, but with 1/2 in front of it. And that's fine with me. So I will not take the steepest descent, but now I will allow myself to get into different directions. So I call this heterogeneity of orientation, which is effective exploration of the ambient space. Now, how do we satisfy this? This is another interesting thing. How do we satisfy this condition? So what is the direction? Yes, so how do I go in a different direction, satisfying, what is this condition? So you see, if P, I wrote it here, is the gradient times the orientation, so omega is on the unit sphere, the d minus 1 unit sphere, and Q is the normalized gradient. Basically, we want this inner product to be a random number normalized between 1 plus m twiddle over 2 and 1. Now, what is this inner product? So this inner product basically represent a spherical cap. And it's in this the question. So we started to discuss, how do you choose? Here's the spherical cap. So if you want, this is the direction of the gradient. If you go in this direction, fine, that's what we had before. But now I'm telling you, you can go in any direction here, and the opening here is all the way to 45 degrees. And I'm allowing you to choose P randomly. How do you choose a random vector on a spherical cap? Well, it's easy to choose a random number, a random vector on a unit sphere, but on a spherical cap, well, you have to do some maneuvering. Before we, you know what? Why won't I do the maneuvering? Okay, so this is the one slide computation of random descent direction. So we go in a random descent direction. That is, we go in a random direction, but I still insist that you will go down. And this is the recipe here. I will not elaborate that because you will see a lot of the literature, they try to do by rotation. The bottom line is, don't do rotation, do reflection. That's what I can tell you. Reflection is better than rotation. It's more efficient. It requires essentially one inner product. Okay, so let me show you the two-dimensional Ackley. So here's the d-dimensional Ackley function, and this is with this randomly chosen directions. And you can see how you see this heaviest element, you see, I mean, this is now faster than before because we have no time, and you can see how they, survival of the fittest, right? Each time the highest is eliminated, and then they try, you see this, now this guy come here, now more mass is going there, this guy is eliminated, now this has become lighter and lighter, more mass is going there, eventually they will be killed, they're eliminated, done. That's it. Okay, so this is the two-dimensional shifted Ackley function, and this is how it works. Now, why randomization is important? So let's take this two-dimensional problem, and we compared the random choice of directions versus the gradient descent. This is interesting. What you see on the top is the SBG gradient descent. What you see at the bottom is this randomly chosen directions. Everything here, which is with light black, gray, is not important. If you have 10 agents in 20 dimensions, you just don't have enough manpower to explore space. You really need to look when the dimension, the number of agents is greater than the dimension. 20 dimension is something I cannot visualize. But you can see that when you have 50 agents, let's say, in the old-fashioned, the old way, I mean, okay, the 12th dimension, it's 100%. 16th dimension, 1%. And now it jumps to 60%. And the same thing from 0 to 21. You can literally see that this randomization allows you to explore space in a more efficient way. Okay. And finally, let me show you then this two-dimensional restriction. I told you that the restriction is more complicated, and you will see it here. Overall, it's much flatter, and there are many more minima at the same height, and they really struggle. So there's a real jungle here, and it goes like this. And you can see that there are many that compete to be now the leader. The leader is not always the minimum. So they change roles here. If you pay attention, they really change role until eventually this guy becomes the heaviest. Of course, once it's the lowest, always mass will go to this guy, and eventually they will all soaked by the global minimizer. And at that point, I'm done. Thank you.